All right, welcome to MA103 Age-Dependent Population Models. All right, so this video, I'm going to go through an example problem where we're going to do this age-dependent model or Leslie matrix. And so I'm not going to read this problem. You should probably pause the video, go ahead and read it over, and then try to solve it, and then watch the remainder of the video to see how I've tackled it. All right, so I'm just going to jump straight into solving the problem. So you might want to pause it and read this. But the first thing I'm going to do is I'm going to define some variables. And again, for the sake of time, I got them pre-typed over here, so I'm going to paste them in. The way that I'm going to do this is I'm going to create these variables a sub n, b sub n, and c sub n, where a sub n represents the number of fish less than 1 year old after n years, b sub n represents the number of fish 1 to 2 years old after n years, and c sub n represents the number of fish 2+ years old after n years. The next thing I want to do is I want to define my vector p sub n. Okay, and so I've got this thing p sub n. Let me make it a vector real quick. Because we've got to state the order that these variables are represented in the vector, right? So I got 3. And so what I'm saying here is that the first row represents a sub n, the second row is b sub n, and the third row should be n, and the third row represents c sub n. Because you can't just assume the reader knows the order that you're going to input these variables into a vector. Okay, and so if that's my vector p sub n, then I can go ahead and give you my initial condition, which is p naught. So I'm going to copy and paste p naught. So we know that we start with 5,000 fish that are less than 1 year old. We've got 0 1 to 2 year olds and 0 2+. All right, so I've got my initial condition. I've got my variables defined. The next thing I'm going to do is I'd have you draw a state diagram, and since I can't draw very well on here, I went ahead and made one in PowerPoint that we can talk through. And so this takes all the given information from the problem, and it says these fish that are less than 1 year old, if they survive, and 70% of them will, then they would go into this 1 to 2 year old state. And if they're 1 to 2 years old and they survive, and 90% of them will, they would go into this 2+ year old state. And if they're there and they survive, and 40% of those will, they stay in this 2+ category, this 2+ state. Now the other thing that we have to model is reproduction rates, right? And so over here, these less than 1 year olds, if they reproduce, and 10% of them do, their offspring would go into this less than 1 year old state. Over here, these 1 to 2 year olds that reproduce, their offspring would go into this less than 1 year old state, and so 80% of them are reproducing. And then lastly, this 2+ year old state, when they reproduce, their offspring goes into this less than 1 year old state, and their reproduction rate is 30%. So this state diagram models all the transitions that would occur in our fish population. The next thing we want to do is we want to develop our transition matrix. And so it may help you to envision something like this, where our transition matrix, we've got, we're moving from a state where our states are these columns to these other states which are depicted as rows. And I've put labels on them so that we can clearly see. So let's take this first arc right here, right? So if I'm in this less than 1 year old state and I reproduce, my offspring goes to the 1 year old state. So that value 0.10 is going to be this first item, right? And if I'm in the 1 year old state and I survive, I would move to this 1 to 2 year old state. Okay, and so with that in mind, I'm going to go ahead and create my transition matrix. But I've got to clear some variables because I was doing other work here in Mathematica. So now my variables are red. Yours should turn blue. So I'm going to say that A is equal to this 3x3 matrix. And I used Control Enter and Control Comma as a shortcut to create rows and columns. So now I'm going to input. So if I'm in state less than 1 and I reproduce, my offspring stay there. If I'm less than 1 and I survive, I would go to 1 to 2, and there's a 70% chance of survival. And I can't go from less than 1 to 2+ in one step, so that's a 0. Right? And so now I'm in this state 1, 2, and my offspring would become less than 1 year old. So there's an 80% reproduction rate. If I'm 1 to 2 years old, I can't stay in that state, so that's a 0. And then if I'm 1 to 2 years old and I survive, I would move to the 2 plus state, and that's probability of 0.9, or survival rate of 0.9. Okay, and now if I'm 2 plus years old and the fish reproduces its offspring, go to this less than 1, and that rate is 0.30. If I'm 2 plus years old, I can't go back in time and get younger. But if I do survive, I stay in the same state, and my survival rate's 40%. Right, so there's my A matrix. The other thing I need is my initial condition, so my P naught. Right, so P naught equals, we've already talked about this vector before, it was 5,000 fish that were less than 1 year old, and that was it. Right, and so I evaluate those, and my variables turn from red to black. Yours should turn from blue to black. And now I'm going to input the recursion equation, which is straight off the formula reference card that says P sub n underscore colon equals A times P bracket n minus 1. And I don't have a D vector, so I'm not going to include that in the recursion equation. Okay, and so that's all I need, and I'll hit Shift Enter and evaluate it. And now I can answer that question, right? If I want to know how many fish I have after 5 years, I'll find P5. Now, if I want to know the fish over the long term, in the long run, I could pick some arbitrarily large number, maybe 100 years, see where my population is, or maybe I want to know 200 years. So I can see that my population is decreasing. I keep going, let's do 500 years real quick. So I'm almost at 0. I have almost no fish, so surely I can't sustain this village. But maybe a better way of depicting the answer here would be in a table, right? So I could make a table, and if I want to make a table of this, of P sub n, I want to change the variable n starting at 0, going to 50. This is how I would input it, and there we go, right? Now I've got a table. I can see that my values are decreasing. But again, it's not the most helpful. So I'm going to teach you guys real quick how to make this plot, right? And so I got to clear a few more variables here that I used earlier, A, B, and C. So I'm going to call A table where I'm going to make a table of n versus P of n. But I want the first item in the list. That's what this double bracket 1 says, the first item on the list. And then I've got to put this other double bracket 1. That removes the parentheses or the curly brackets from the list value. Okay, and so I want that. I'm going to start at, I'm changing the variable n, starting at 0, going out to 100. Let's just see what this looks like. All right, so this first column is the year. This is my population of fish less than 1 year old. Okay, and so I'm going to go ahead and suppress the output real quick. I'm going to do the same thing for my variables B and C. But since I've already got this table command typed out, I can just copy and paste it. Copy this. But instead of the first item in the list, I want the second item in the list. That'll be my 1 to 2 year olds. If we want to verify that, the first year we didn't have any 1 to 2 year olds, and then we start getting them, right? Okay, and then we're going to do the same thing for our 2 plus year olds. Oops. We'll paste the same command, but again, we don't want the first item in the list. We want now the third item in the list, and we can evaluate that. So if we're going to create a plot, the way we do the plot command is list plot, and we want to make a plot of A, B, and C. Let's just see what that looks like real quick. So there's our plot. If we want to clean this up a little bit, we can do that. We can add axes, label the axes, right? So we're going to label these, and the way we do this is we're going to label the x-axis first, so that is year, and our vertical axis is the number of fish, maybe. and close off my list. Let's just check that. Okay, so I see year down here, number of fish, and then maybe we want to add a legend, right? So plot legend, and so we're going to do this in the same order that we listed these variables, right? So the first item in here was less than 1 year old, and then we had 1 to 2 year old, and then 2+ year old. Close our list, and let's check this out. There we go. Now we've got a legend. We can see what's going on. If we wanted to make this plot go further out, we could. We can just change these numbers from, instead of 100 years, we can go out 500 years. We can evaluate all these things. Now we go out 500 years and we can see what's happening. Right? All right, there we go. So hopefully that helps you out, helps you understand age-dependent population models, and gives you some instructions on how to create tables and generate plots.